All right, today we're going to do a deep dive, a real systems-level analysis of a fundamental actuator control system. Now, don't let the small scale fool you. The principles we're covering here, they're the absolute bedrock of modern automation. You'll see these same concepts at play everywhere, from a benchtop prototype like this one, all the way up to the heavy machinery you'd find on a factory floor. So, let's get started.
So, we're going to follow a really logical path here. In fact, it's the exact same signal flow you'd find in any standard industrial control system. We'll kick things off with the big picture, the system architecture. Then we'll trace the signal from the input, through the control logic, see how it drives the physical output, and finally, we'll cover the absolutely critical step of data logging. You gotta verify your work, right?
Okay, first things first. We need to lay down the foundational structure. Think of this as the blueprint for the entire operation. It's what governs how a system takes in a command and, actually turns it into a physical action.
All right. So at the very core, every single robust control system you'll ever encounter operates on this fundamental loop: input, processing, and output. It's that simple. An input signal comes in, that's the command. The processing block crunches the numbers and calculates a response. And then the output stage makes it happen in the real world. And listen, this isn't just a suggestion, this is the universal framework for control systems engineering. We're also going to tack on that critical final step, logging, because if you can't verify the result, you're flying blind.
So let's start with that very first block in our architecture, the input signal. This is where the magic begins, really. It's the stage where we take an operator's physical intent, turning a knob, pressing a button, and translate it into clean digital data that the processor can actually understand.
In the system we're looking at, our human-machine interface, the HMI, is a simple 10 kilo-ohm potentiometer. Now, it might look basic, but its function is absolutely critical. As an operator turns that knob, it's acting as a voltage divider. What that means is it's putting out a continuous analog voltage that is a direct, precise representation of the position they're commanding.
But here's the thing, that smooth analog voltage, it's completely useless to our digital processor. It's speaking a different language. So we need a translator, and that critical translation is performed by an analog to digital converter, or ADC. What this little component does is it samples that continuous physical signal and chops it up into a discrete digital value, a number, that our control logic can finally work with.
And this brings us to a really key system parameter, resolution. The ADC in this microcontroller has a 10-bit resolution. So what does that actually mean? It means our entire 0 to 5 volt input range gets broken down, or quantized, into 1024 distinct steps, from 0 to 1023. This number is a huge deal because it directly dictates the precision of the entire control system. The higher the resolution, the finer the control we can achieve.
This table right here shows you exactly how that translation works in practice. So, as the wiper on the potentiometer moves, the voltage changes in a nice linear way, and you can see how the ADC maps that voltage to a specific digital number. For instance, look here. A 50% turn gives us 2.5 volts, and the ADC spits out a digital value of, well, roughly 511. That integer, that number, is what our control logic is going to use.
Okay, so we've got our clean digital input. Now it's time to move to the processing stage. You can think of this as the brains of the whole operation. This is where that raw data gets transformed into a precise, actionable command that we can send out to the actuator.
The control algorithm itself is pretty straightforward. It just follows 3 logical steps. Step 1, it grabs that raw sensor data, our number between 0 and 1023. Step 2, it scales that number to match the physical range of our actuator, which in this case is 0 to 179 degrees. And finally, step 3, and this is so important for safety and for the life of your equipment, it constrains that value. It puts a hard limit on it, making sure it stays within the actuator's safe operational limits, which we've set to 0 to 90 degrees.
And right here, you can see the direct implementation of that logic in code. That map function, that's doing the scaling for us. It's remapping the input range, 0 to 1023, to our desired output range of 0 to 179. Then, that constrain function kicks in. Think of it like a safety clamp. It guarantees that no matter what the mapped value is, the final command we send to the actuator will never go outside that safe 0 to 90 degree window. It's a critical safety net.
So you might be wondering, how do we actually tell the motor to go to that final angle? Well, we do it through something called pulse width modulation, or PWM. With a servo, the position isn't determined by how much voltage you give it. No, it's all about the duration of a high voltage pulse.
For example, a 1 millisecond pulse tells it to go to 0 degrees. A 2 millisecond pulse tells it to go to 180 degrees. And this all happens inside a repeating 20 millisecond cycle. This is, for all intents and purposes, the standard language of servo control. All right, that brings us to the output stage. Actuator drive and stability. This is where the rubber meets the road, so to speak. It's where our digital command finally becomes physical motion. And let me tell you, this is where solid electrical engineering principles become absolutely critical for reliable operation.
So, the actuator in our system is a standard hobby servo. Its job is really simple but important. It just listens for that PWM signal from the processor, and then it translates the length of that pulse into a very precise angle, physically carrying out what the operator wanted in the first place. Okay, now we need to talk about something that is a non-negotiable principle in industrial automation and robotics. I'm talking about power domain isolation. Look, motors are electrically noisy. They draw huge, spiky, fluctuating currents. If you try to share a power supply between your sensitive control logic and your power-hungry actuator, well, you are just setting yourself up for system failure. It's a recipe for disaster.
And this slide really lays out the consequences of your power architecture choices. On the left, you see the wrong way to do it, a shared power supply. This leads to all sorts of problems. Voltage sags, your microcontroller browning out and resetting, and that awful, unpredictable jitter in your actuator. Now look at the right side. This is the correct architecture. It uses isolated power supplies that only share a common ground reference. And what does that get you? Stable power, reliable logic, and smooth, predictable motion. It's the only professional way to do it.
Which brings us to our final stage. And honestly, from a professional standpoint, this might be the most important one. Data logging. I want to be really clear about this. Logging is not an afterthought you tack on at the end. It is an essential engineering tool for verifying your system, for diagnosing problems, and for tuning performance.
You know, there's an old engineering proverb that is just so true here. If you can't measure it, you can't improve it. And that's the bottom line. Without hard, empirical data, any attempt you make at improving your system, at debugging it or optimizing it, it's all just guesswork. Measurement is absolutely fundamental.
So a robust data logging protocol involves these key steps. First, we're using the hardware SPI bus because it's fast. Then, in the code, sd.begin is what kicks things off and initializes the interface with the SD card. sd.open then creates our log file, or opens it if it's already there. Datafile.print is what actually writes our data to the file. And then, this is the part people sometimes forget, but it's critical, you have to call datafile.close. That flushes the buffer and makes sure everything you thought you wrote is actually saved to the card, ensuring data integrity.
And this is what you get for your efforts, a clean, beautiful, comma-separated value file. You can open this in any spreadsheet program. Each row is a perfect snapshot in time, logging the timestamp, the raw sensor value, and the angle we commanded the servo to go to. With this data, an engineer can plot the system's response, they can identify any lag, and they can verify with certainty that the actuator is doing exactly what it's being told to do over time.
So to wrap this all up, the core principles we've just walked through, input, processing, output, power stability, and logging, are truly universal. These aren't just little tricks for a benchtop model. They scale directly, one-to-one, to the most complex systems you can imagine. CNC machines, massive automated assembly lines, and high-precision industrial robots.
And that leaves us with one final thought to consider. The difference between the simple model we've looked at today and a multi-ton robotic arm that can move with sub-millimeter precision, well, it's not a difference in principle. It's only a difference of scale and tolerance. So the question is, how do these exact same fundamentals, command, action, and verification, scale up to achieve that incredible level of industrial performance?